So this is the Fourier Series Part 3 lecture for ECE 343. I think I'll call this one Better Living Through Orthogonality. We've looked in the past lectures how orthogonality can help us make an estimate of an object of interest. There's the idea of the orthogonality principle, which basically stated that if you make the error of your estimate orthogonal or at right angles to the building blocks, it's supposed to be optimal. We gave that without proof. Well, today's the proof. So we could also call this lecture the proof of the orthogonality principle. That doesn't quite have the same ring. We do like the idea of having something that is optimal, though, right? We would like to do things as best we can. And we just want to make absolutely certain that this principle that we had shown before without proof, this orthogonality principle, really delivers on its promise of minimizing the norm squared error of our estimate. So let's jump right into it. This one is a lecture that I basically pre-written because a lot of it is just a bunch of mathematical proofs. And with it being pre-written, we can maybe not be so distracted with my writing and spend more time just focusing on the basic ideas and steps. We will make some reference to the second page, so refer to that second page of the Fourier series formula sheet that's available on the class website. That second page has a column for linear vector spaces, and it also has a column for the orthogonality principle. We're going to be making reference or some connection to the ideas on that, and we'll need to have that handy when we go through this proof. So what is it that we were trying to do in general? The idea of a couple lectures ago was that we had some object of interest, right? So I'm going to go ahead and just draw our coordinate analogy of this guy. So we had the Cartesian plane and we had some object of interest. We could call that guy x, right? So you could think of that as being a vector in that Cartesian plane. And we wanted to estimate that using a linear combination of building blocks. So we had some building block. I'm just going to draw one for right now, some phi1. And we ended up scaling that, right? So that we got some c1 times phi1. And we wanted that scale factor c such that that estimate, which is what that whole thing was equal to, the estimate of our signal, some linear combination of building blocks, was as good as possible estimate for the object of interest x. In this particular case, this dotted line I've drawn here is the error, right? That error is x minus x hat, or you could do it the other way. And we know that that error is minimized as long as the error was orthogonal to or at right angles to the building block of interest. So that was a lecture in very quick summary that we had done before. We have an object of interest, x. We want to estimate it using a linear combination of basis functions, and we do so in an optimal way by ensuring that the error is orthogonal, so at right angles to the building blocks. That's a snapshot for the orthogonality principle. So let's go ahead and cast this in terms of something with more than just one piece and not in the Cartesian plane. This is going to be using basic functions. So we'll start up here that we're going to allow ourselves an estimate. I'm going to call that x hat sub k with a perp symbol up in the upper right. And basically, this is just saying we're going to estimate an object x. How are we going to estimate it? We're going to estimate it using a linear combination of basis functions phi sub k. So I'm going to sum from k equaling 1 to cap k of these phi k's, each weighted by an unknown coefficient ck, and it's also going to have that little perp symbol up there. Why am I putting these perp symbols up there? Because this particular estimate, I'm gonna go ahead and take the estimate that we are trying to prove is best. We're gonna let this estimate be the one that satisfies the orthogonality principle. So when I have that little perp symbol up here and I have that little perp symbol up there, it's just saying that we are going to be constructing an estimate that is assumed to satisfy the orthogonality principle, this thing that the orthogonality principle says is best. What was the orthogonality principle? It said that the error x minus x hat, right, had to be orthogonal to, that means its inner product has to be orthogonal to the basis functions, phi sub l. So the error inner product with the basis functions has to be equal to 0. That's the definition of orthogonal. And we have to do that for all the basis functions. The orthogonality principle said if you had that, you were supposed to minimize the norm squared error. We had never proven that we minimize the norm squared error by satisfying that. We're trying to do that now. So I'm just going to be looking at the estimate, right? The estimate in this particular case that satisfies that orthogonality principle. just to make sure that we don't confuse this estimate with any other. And we are going to be looking at a generic estimate. That's how we're going to end up proving that the orthogonality principle is best. We're going to have a case of an estimate satisfying the orthogonality principle, and then we're going to look at everything else, and we're going to prove that everything else has worse performance. Just to make sure that this orthogonality principle estimate is not confused with that generic estimate, I've gone ahead and also written that estimate x hat in red, just making sure that that red variable designation here is to highlight this is the one that we are trying to say is best. So we started out by saying, let's go ahead and think about having in hand this estimate that satisfies the orthogonality principle. That is making the error orthogonal to the data. What are we going to do with that? We're going to compare it performance-wise to an arbitrary estimate. So we're going to look at an arbitrary estimate. That arbitrary estimate we can just call x hat sub k, so a k-term estimate. That k-term estimate, if you wanted to, we could break that out in the kind of sort of normal way. It's a summation, k equaling 1 to cap k of some ck's, phi k's, right? So it has the same exact structure. It's just that we are not going to require that this one satisfy orthogonality. We are making no statement that its error has to be orthogonal to the data. And all we're going to do is we're going to take a look at this guy's norm squared error. I would like to take a look at its norm squared error, and I would like to be able to show that the norm squared error of this guy always has to be greater than or equal to the norm squared error of the estimate that satisfies orthogonality. We've made no particular statement as to the structure or the conditions for this arbitrary estimate. It could be anything. So completely open as far as that, as long as it is arranged as a linear combination of those basis functions. Okay. So what's the norm squared error? We know the norm squared error. We call that some epsilon sub k or some cap epsilon sub k. This error sub k, a k-term error, is just the difference between the object and the estimate. So x minus x hat, and then take its norm squared. Okay. So this is a measure of the size of the error. Norms give us a measure of size. And we're going to do a very kind of simple technique that is done oftentimes in mathematics. It's a technique called a little give and take, you might say. And so I'm going to take this same error that we had just looked at, that norm squared error of an arbitrary estimate, and I'm going to insert our orthogonality principle estimate, and I'm going to take it away at exactly the same time. This might seem very odd to be doing, because really in the end I've done nothing, right? I've added something in and subtracted it out. That's like adding in 0. That's how I know that it still is equaling EK off on the left. I haven't changed that particular quantity. But this strategy, this technique in mathematics, is going to give us a way of inserting this thing that we're interested in, this estimate that does satisfy the orthogonality principle. I'm going to then group things just a little bit creatively. I'm going to go ahead and take the x that I had before, right? So we had our x before, and I'm going to go ahead and group it with the minus x hat perp k, and I'm going to call that my a, okay? And then I'm going to go ahead and take that other side that was originally in there, that's the minus x hat k, that was minus the arbitrary estimate, and I'm going to group that with the x hat perp k, and so that is going to give me this thing that I'm going to call b. Okay, so what do I have? I have this norm squared error. The error of my arbitrary estimate is going to be equal to the norm squared of a plus b, where a and b were defined above. Well, what is a norm squared? We had seen this before in our properties. So if you go back to that Fourier Series second page, you'll notice in there that when it talks about norms, it says a valid norm is an inner product, or an inner product is a valid norm. So this norm squared here, I'm just going to take as being the inner product of this thing that we have, a plus b with itself. So inner product of a plus b with a plus b is the norm of a plus b squared. So I'm just going to turn that error size into an inner product, because inner products are just going to give us a little bit more flexibility in moving forward. What is the inner product of something with itself? Well, we also have properties of inner products, and we know inner products of sums can be written as sums of inner products. So I can FOIL this guy out, right? I can distribute this out. I can take inner product of A with A, right? I can take inner product with B, right? I can take an inner product of B with A, and I can take an inner product with A and B, something along those lines. So I'm going to get four terms in here. The inner product of A with itself is just the size of A squared, right? The norm of A squared. Same way, the inner product of B with B is just the norm of B squared, something along those lines. And then we get these kind of cross terms. We're going to have the inner product of A with B, right? That's the outside of that distributed part out, if we take a look at that again. And then we have the inner product of B with A. That's the inside terms that were FOILed out, that were distributed out. So this size squared, right, A plus B norm squared, which is a representation for the error of my arbitrary estimate, can be represented using four terms. I'm now going to resubstitute in what was A and B. So norm of A squared is just going to be this norm of x minus x hat perp k. The norm of B squared is just going to be the norm squared of x hat perp k minus x hat k. And then I get all the cross terms. And the first term in there is going to be x minus x hat perp k. Inner product with x hat perp k minus x hat k. That's this first one. That's the inner product A with B. And then we just reverse or exchange the order of those guys, and I get the last inner product that's involved in there. And so I'll leave that as well. Okay, well, we have another property that we're going to make some use of now of inner products. It's the first inner product property. If you go back on the sheet, it's the one labeled 1. And that's that the inner product of A with B needs to be equal with the inner product of B with A complex conjugated. That's a requirement to have a valid inner product. So I'm going to take a look at these two middle inner products, right? One is an inner product of A with B, one is an inner product with B with A. That means that the second one, right, this second one sitting in here, had better just be equal to the complex conjugate of the first one, something along those lines. And what do I know when I add something to its complex conjugate? If you add something to its complex conjugate, you get twice the real part of whatever it was that you started out with. So we know just from our study of complex numbers that if you had a complex number and you added to it its conjugate, that's equal to 2 times the real part of W. So I'm going to be able to turn this double sum here, right, that I have this sum of two inner products into twice the real part of just one of those inner products. And I'm going to do that just because it's going to allow me some simplification here. So let's go ahead and do that. I still have my norm of A squared, which is now in terms of x and x hat perp, and I have this other norm of B squared. You can make the substitution in there as well. And then those two middle inner products, the cross ones, the A with B and the B with A, I can write, because one is just the conjugate of the other, it is twice the real part of the first one, which was the inner product of x minus x hat perp k, right, with x hat perp k minus x hat k, something along those lines. All I'm doing here is I'm playing some mathematical games on this overall error for an arbitrary estimate. I know where I'm going with this. I've done a little give and take so that I can insert this quantity of interest, this estimate that meets the orthogonality principle, and I've been doing some simplification based on a variety of properties that I have at my disposal. So now we're going to start working on trying to simplify this so that we can hopefully build some insights. One of the things I'm going to note is that any estimate, so those things that have a hat, whether it's the arbitrary estimate or the one that satisfies the orthogonality principle, we know that either one of those, because they're the estimate, and these estimates are constrained to be linear combinations of building functions or building blocks, these basis functions, the phis, either one of those guys are going to be linear combinations of those building blocks. That's all they have in there. When it comes to an actual function, in our case, it's going to usually be a function of time. The only thing that is the function of time in there are going to be the phis. So what do I know? Going back to this middle term, I'm focusing on this guy right now. I'm going to look at the first argument in there, this first argument. That first argument is x minus x hat perp k. What is that? That's the error, right? That's the error of my orthogonality principle. It's the error of my orthogonality principle estimate, something along those lines. And I'm going to be inner producting that, right, with something that only has phis in it, okay? It's just a sum of scaled phis. Well, what do I know about my orthogonality principal estimate? By construction, the error, right, of my orthogonality principal estimate, inner product with those basis functions, has to be zero no matter which basis function you're looking at. And that means that the error, right, is going to be orthogonal to any linear combination of these basis functions as well. Since this second piece over here, this guy right here, is just a linear combination of basis functions, and this first piece here is just my error, I know by constraint, by default, that that inner product must be equal to zero. Okay, so what do we get? We get that this term, that twice real part of the orthogonality principle error with things that only depend on the phis must be equal to zero. You can also get part of the details in here by go ahead and plugging in for all of those terms. You're going to get some sum of some other coefficients. Let's call them ck primes with some phi k's, something along those lines. And we know that inner products of sums can be broken out to sums of inner products, and the result falls almost immediately. So that middle term, by construction, just disappears. Okay, that greatly simplifies things. So we're going to go ahead and look at the simplification. We get then, right, that the overall error, the size of the error, if you will, of my arbitrary estimate is going to have the basic form of the object of interest minus that estimate norm squared, right? That's the definition of what error is. It's just looking at the size of the error. And if we go back to what we had before, right? We had seen four terms, those four terms, there's the four terms, those four terms became three terms, and those three terms, because the middle term was zero, became two terms. We end up with just these two terms. We get this first piece, which is really just what? It's just the error of my orthogonality principle estimate plus the norm of something else. And norms, right, norm squareds, must be non-negative things. So it has to be, that second term has to be greater than or equal to zero. So does the first one. Okay, so what can I say about that? I can say that this arbitrary estimates error, right, is equal to a sum of these two pieces. And we know that this first piece, right, is just the error of my orthogonality principle estimate, and we're adding to that something greater than or equal to zero. That means that this overall error has to be greater than or equal to just the orthogonality principle error by itself, right? Because why? Because this arbitrary error, right, this arbitrary size, the error of the arbitrary estimates, the size of the arbitrary estimates error always has this extra piece to what the size of the error of our orthogonality principle is. This is actually the result we wanted. So ta-da, guess what? We get that the error or the size of an arbitrary estimate is always greater than or equal to the error, right, that results from the orthogonality principle. The error of an arbitrary estimate, right, can never be less than the error of our orthogonality principle estimate. That tells us, that statement by itself tells us that the orthogonality principle does provide the optimal solution, right? The orthogonality principle is indeed the optimal estimate. So the orthogonality principle, x hat perp of k, gives the best performance. It gives us the smallest error that we could possibly consider. Things get even better though, right? So let's take a look again at that arbitrary estimates error. That's the E sub k. We know that it's at least as big as the error associated with the orthogonality principle estimate, right? And then we get this extra term. That was that inner product of b with b, and then we resubstituted in what was b. We know the norm squared of anything is always greater than or equal to zero. If you look at the fourth property of inner products, the inner product of something with itself is always greater than or equal to zero. That's part of it. But then the other part is it says it equals zero only if the thing inside is actually equal to zero. So the only way we can force this second term to be zero such that the estimate of an arbitrary estimate matches exactly the estimate given by orthogonality principle is if x hat k is equal to x hat perp k. That's the only way we can get this middle part equal to 0, and that's the only way that you can actually get the equal part to make that second term equal to 0. So this is like a double ta-da, right? This is like a super extra neat result that we already knew this, that the error of an arbitrary estimate, right, is no smaller than the error of the orthogonality principle estimate, and it equals it if and only if the estimate is the orthogonality principle estimate. What does this really tell us? This tells us that the orthogonality principle estimate, x hat perp of k, uniquely, right, gives the best performance. So not only does orthogonality give us the best performance, it's uniquely best. There's nothing else that is just as good. It is the sole winner. It's going to always win the gold medal here. So this is exactly what we wanted to prove. We've done it in a very kind of simplistic way. I'm going to recap that right now. What did we do? We said, let's take a look at an arbitrary estimate, x hat. Let's look at its performance, E sub k. That performance with a little give and take, we represented into some terms that included the performance of this thing that we said was supposed to be best, the orthogonality principle estimate. We found that the error for an arbitrary estimate could be no smaller than the performance or error, right, the size of the error, for the orthogonality principle estimate. And in fact, the only way you could be equal was if your arbitrary estimate was the orthogonality principle estimate. Since nothing is smaller, we know that we have optimal performance from this orthogonality principle driven estimate, and we know it's unique from this second double ta-da kind of result. Okay, a final note that we might do, this is the last part of the column 2 that talks about the orthogonality principle. If we take a look at the size of the error that we get when we use the orthogonality principle, we already knew that was the minimum kind of error size that we could get. So I could also call that E sub k min. It's the minimum value. What does that guy look like? Well, the size of the error is just the error, right, inner product with itself. That's how we get a size squared. I can, again, use my knowledge of inner products, right, and I can do my distribution here. I can take these terms and I can distribute them out. So if I look at the first one, actually probably don't have to distribute all of them. I'm going to just distribute a portion of them. So I'm going to go ahead and take this first term and I'm going to distribute and take it with the inner product of that guy and then subtract from it the inner product of that guy with the second piece. So first one in here, I'm going to take the error, right, and inner product it with x. That's this piece. And then the second arrow that went down this way was just going to be the error inner product with the x hat perp k, and then the minus sign can be pulled out. So that's the second piece. So our minimum error, right, is equal to, well, there's something here about the error inner product with x minus, right, the error inner product with our estimate, x hat perp, which we know is only made up of phis. And because we have an error, right, inner product with something that's only phis, and the error here is for our orthogonality principle estimate, which says the error must be orthogonal to or right angles. Its inner product with the basis functions must be 0. We know we get 0 for that whole thing. So what does that give us? That gives us that the error, right, for orthogonality principle estimate, or the minimum error that we can possibly get, is going to come solely from this first piece. Now we can distribute that second piece out. We're going to get the inner product of x with itself. That's just the size of x. And then I'm going to subtract from that the inner product of x hat k that meets the orthogonality principle, my orthogonality principle estimate, right? Inner product with x. Okay, and what do I know that piece is? Well, that if you go through that second column of the formula sheet, this piece right here is just a sum from 1 to k of my ck inner product with phi k and x. You can actually get that just by substituting in what is this guy. What is this guy? It is a summation, right? K equaling 1 to cap k, and I have my c sub k because they meet the orthogonality principle. We said we'd notate that with a perp, and we have the phi k's in there. So if I plug this whole thing into that, And then I use the properties of inner products, that the inner product of a sum is just the sum of the inner products. I can get this result here. So it's just another convenient way of finding out or calculating out what's the amount of error that we'd expect given a particular estimate. What you might notice in here is that we usually know how big is the thing that we're interested in, right? And we know things like our basis functions. We know what it is we're trying to estimate. So this piece here is known. We went ahead and solved for some coefficients, and we can, through a pretty simple set of calculation, use those coefficients to find out what's the total amount of error. What does that tell us? As the error goes down, right, we know that the difference between our estimate and the signal of interest is going to get smaller. You could even note that visually. You'll just see them getting closer and closer visually to one another. We'll take some additional looks at that as we go along as well. Okay, so we have at this point gone through an entire proof to show the optimality of the orthogonality principle, that an estimate that follows the orthogonality principle is indeed the best estimate, best as measured by minimizing the norm squared error. We're ready. Well, we're finally ready with all this math in place and proofs complete. We're ready for the complex Fourier series. And we'll derive it using the orthogonality principle. We've gone through a couple lectures now just putting the background mathematics in place so that we can handle with absolute confidence the derivation of this thing called the Fourier series and know what it is doing, and that it's doing a really good job because it is an optimal solution. So let's set this up. This will go quick now. If you have been a little bit overwhelmed by just all this background in here, the result that we want comes out super simply once we have all this background math in place. So we're going to go ahead and derive the complex Fourier series. Let me make just a very quick comment about this term complex, right? This is a misnomer, like so many things that in this class use the word complex. This is just indicating that our basis functions, the phis, are going to be complex exponentials rather than the trigonometric functions. So there is a trigonometric Fourier series. There's a compact trigonometric Fourier series. Those are ones that the book tends to prefer. And there's this one called the complex Fourier series. This just means that our basis functions are going to be the complex exponentials rather than the trigonometric form. You're going to go through Euler's, conversion to get those exponentials into trigonometric cosines and sines. To put it a different way, even though we're using complex exponentials, the mathematical manipulation using this particular form is way easier than the trigonometric form. So if this was more aptly named, they wouldn't call this the complex Fourier series, they'd call it the easy Fourier series, because when we use basis functions that are these complex exponentials, they are mathematically far easier to manipulate than the trigonometric form. It's one of the reasons I prefer it. Okay, so let's go back to what Fourier's big idea was. Fourier's idea was that you could have a signal, right, and we could estimate it using a linear combination of complex exponentials. That was Fourier's big idea. You represent a signal as a sum of sinusoids. Nice idea. Turns out this is exactly constructed in the way that we know how to get the very best estimate, how to make one that actually minimizes the norm squared error. So Fourier's big idea again, what was it? It was, let's go ahead and build or estimate some object x using because we're looking at a periodic signal, using harmonically related complex exponential basis functions. So these complex exponentials, those are our phis. The cap x sub k's are going to be the unknown coefficients, linear combination of those to give me an estimate of that overall periodic function, something along those lines. We want to find those cap x of k's. We want to find cap x of k for however many we choose to put into our sum. Later, we'll find out that we're going to let cap k go off to infinity. That's going to make sure that we get a really good estimate. In fact, it will converge towards the signal of interest. But for right now, let's just leave those as a finite number of terms in my series. That means I'm probably not going to be quite perfect. That means that there would be some error. So we want to find these coefficients, right? We want to find these coefficients that minimize the overall error of the estimate. And we are gonna measure the size of this error using a power idea. So we're gonna say, let's minimize the power of the error. What is the power of the error? Well, we first look at the error, right? That's x minus x hat. We're going to magnitude square it so that it's always positive, and then we're going to integrate it over a period and divide by a period. That's just the definition of power for a periodic signal. If you have a periodic signal and the error itself is also going to have to be periodic, the power of a periodic signal is just a normalized integral over the period of that signal. In this case, it's going to be the error squared taken. Okay, so we want to find coefficients that minimize the power of the error. That seems like a pretty sensible thing, right? If we could minimize the power of the error, or better yet, if we could drive the power of the error to zero, right? That means whatever our estimate as far as a power view would be identical to the signal of interest. We'll talk more about that perspective when we talk convergence of the Fourier series coming up in a later lecture. So just a reminder here, we are dealing with a signal x of t that is assumed periodic. We're going to go ahead and give it a period cap t naught, which is reciprocally related to its radiant frequency omega naught. And by construction, right, because our x hat of k is a linear combination, if we go back up here, it's a linear combination of exponentials, and each one of those exponentials are just integer multiples of that base frequency omega naught. They all share the same period. By construction, our estimate is also t periodic, okay? So Fourier's big idea, estimate this object of interest, in our case a signal, a periodic signal, using a linear combination of basis functions. The basis functions we are choosing here are complex exponentials that are harmonically related. That ensures that it stays periodic as it needs to be. Why do we pick exponential basis functions? Because they behave beautifully for systems and signals. We have spent almost the whole semester developing those relationships. You put an everlasting exponential in, you get an everlasting exponential out, modified by that complex constant cap h, the system transfer function. We know exponentials inside and out. We know that they're easy when it comes to system analysis. We're really happy to break up a signal in terms of its exponential components. We've talked about that before. So we want to find these coefficient cap x of k's. Those cap x of k's, by the way, those guys right there are called our Fourier series coefficients, right? We're trying to build a Fourier series. The Fourier series is just the estimate itself. So this guy right here is our Fourier series. The Fourier series is a sum of a bunch of harmonically related guys, each weighted by these Fourier series coefficients. We're looking for the Fourier series coefficients, and we want to do it such that we minimize the power. That's a constrained optimization problem, and we know how to solve it such that that power is minimized. We use orthogonality, better living through orthogonality, right? We can get the very best, it should be called best living through orthogonality, right? We are going to get those best coefficients by satisfying the orthogonality principle. So just making sure that we've got all the pieces in place so that we can just go ahead and use that orthogonality principle. We know that the basis functions in this particular case are functions of time, and they are these harmonically related exponentials, okay? It's outside of the scope of this particular lecture, probably this class, to really talk about the construction of basis functions or complete bases for a particular linear vector space of interest, but it turns out these complex exponentials do form what is called a complete basis for the signals of interest for us, those ones that are periodic power signals. So the error, right, is just going to be a difference between the signal and the estimate, norm squared, and we know that that norm squared is going to be related to power. So 1 over t naught integral over any interval t naught, right, of that absolute value squared of x minus x hat, the errors squared. So we can really back out of this an inner product. We need an inner product that results in that kind of norm squared. An inner product that does that is to just take 1 over the period, integrate over the period of the first signal that we're inner producting with the conjugate of the second signal. So the inner product between x and y would be 1 over t naught integral over t naught x y conjugate. Now, what do I know a norm squared is? I know a norm, right, of x squared is just the inner product of x with itself, and we just adopted this thing as 1 over t naught integral over t naught of x times x conjugate. Well, that's just size of x squared dt. That's power of x. That's exactly like we saw. So we went through it a little backwards, but we can construct an inner product that is consistent with this power idea, which is the thing we're trying to minimize. So the last little bit, and really this is for the exceptionally curious, this inner product of x of y is on the linear vector space of functions that are square integrable over interval t naught, okay? And it's probably periodic functions that are square integrable over interval t naught. That's just mathematical completeness. If you're not that curious, don't get too hung up on it. So for this inner product, note that our basis functions, we already said what those were those harmonically related complex exponentials. They are also orthonormal, okay? You're going to get a homework problem on that. It's not hard to show, okay? Orthonormal, what does orthonormal mean? The ortho part, right, says that the inner product of one basis function with any other basis function is equal to zero. That the different building blocks in our system are at right angles to one another. So the inner product with phi L and phi K is equal to zero basically when K is not equal to L. If I'm looking at one basis function and another one, their inner product is equal to zero. That is true for these harmonically related complex exponentials. Again, this will be something you'll prove in the homework, not a hard proof. The normal part means what? The normal means unit sized. So the size of these building blocks is 1. That means that when k equals L, when I take the inner product of a basis function with itself, that's just saying the size of that basis function, it turns out to be 1. Why do we like that? If you go back to that second column on the Fourier handout sheet, when it talks about the orthogonality principle, if I have orthonormal basis functions, the ortho part lets us solve for each coefficient individually. The normal part means you don't have to do that end division. You save yourself an extra step in the mathematics. So how do we solve that optimization problem? We apply the orthogonality principle. Because they are orthogonal, we can solve, right? We can solve each x sub k individually. Because of the normal part, normally even when we had just the orthogonal part, we get x of k as being the inner product of x with phi k over the size of phi k squared. But we just said that those guys were 1. So what do we get? We get that those best coefficients can be found individually, and they can be gotten as an inner product. That's a projection, if you will, of the object of interest x onto the building block, the basis function, phi sub k. Oh, we are there. So how do we get these best coefficients? The Fourier series coefficients. We just take the inner product of the object of interest x with the basis function. What was our inner product? It was 1 over t naught, integral over t naught, the first argument, x of t, times the conjugate of the second, right? We need that conjugate relationship. So instead of e to the jk omega naught t, we need to take its conjugate. So we get an ejk omega naught t with a minus sign, right? There's that minus sign that came out of the conjugate part of our definition of our inner product. And we integrate over all time. This is the Fourier series analysis equation. It tells us how do we compute those coefficients, right, such that we get this beautiful, right, construction estimate of my signal as a linear combination of harmonically related complex exponentials. So this was the Fourier series synthesis equation, or just the Fourier series, if you will. It says any old periodic signal can be represented, right, as a sum of scaled harmonically related exponentials. We needed to find those scale factors, and those scale factors come out easy. Those scale factors, right, are just from an inner product, a projection, if you will, of x onto the phi k. So I take 1 over the period, integrate over the period, the signal times the conjugate of my basis function, e to the minus jk omega naught t dt. That is the Fourier series analysis equation. Okay, so we have done probably just a good deal of derivations at this point. Probably a good place to stop. Next lecture, we will get more into the practical matter of things. We'll start using these things that we've learned so that we can analyze signals of interest. So next time, it's all going to be about computing and working with these Fourier series in a much more kind of tangible, hands-on. We're gonna get away from all this mathematics. We had to do the mathematics so that we knew that we were moving forward in a very understandable way, and knowing that they were optimal in the way that they claim to be. Now we're ready to get our hands dirty and actually get them to work. So next time, I promise much more just computing and applied.